Okay, the other thing that we did in class number 2 was the following problem. We had Farmer Dave and his two types of fertilizer available to us, Super Grow and Crop Quick, and they have different costs, and he's trying to minimize his overall cost while still meeting his field requirements. So let's use this space to write out the LP. First of all, define our decision variables. We'll let x1 equal the number of, try this again, bags of Supergrow, and x2 will equal the number of bags of the other stuff, Crop Quick. And his objective is to minimize his overall cost. So minimize Z equals, we know the Supergrow and the Crop Quick. So this contributes $6 to the cost every unit of X1, and $3 is contributed to the cost for every bag of X2. And we have some constraints. We're subject to a couple of constraints. Nitrogen constraint. We can see here the chemical contribution, and we can use this in our constraint. So a bag of X1 contributes 2 units of nitrogen, and a bag of Crop Quick contributes 4 units. And the number of units has to be greater than or equal to the minimum required, which is up here, 16. And again, you can check your units of measure. This is 2 pounds per bag times bag leaves me with pounds. This is in pounds. Everything's copacetic. And we have our phosphate constraint. And again, 4x1 plus 3x2. These values here are greater than or equal to 24, which comes from our problem above. The last thing to consider is our old friend non-negativity. So we have x1 and x2 are both greater than or equal to 0. So we have 2 decision variables. We can solve this graphically in the first quadrant. So here we go. Looks like it's all going to fit on there. So again, we want to plot the lines, say 2x1 plus 4x2 equals 16. And once we plot the equal side of the line, then we can do the less than or equal to, or sorry, we can do the greater than or equal to side, come up with the feasible side of the line, and repeat for everybody else. Once we have all the feasible sides, we get over the feasible region. So again, we can set x1 equal to 0, solve for x2, 16 divided by 4, set x2 equal to 0, and we get 8 over here. So let me just draw a line, 1, 2, 3, 4, over 0 up 4, and over 8 up 0. That looks like the first line. Let me just change my color of my pen. We'll do the second constraint in blue so that it's nice and consistent. And the second constraint was 4x1 plus 3x2 is greater than or equal to 24. And again, set x1 equals 0, solve for that, and we get 8. Set that go to 0, solve, and we get 6. So there's 0, 8, and we go down here to 6, 0. And we're interested in this side of the line. And we're interested in this side of the purple line, of course this side of the axis, and this side of the axis. The next thing we need to do is plot an objective function line. And we have z equals, what was it, 6x1 plus 3x2. And find a convenient value that works with these coefficients. We can choose any value we want for z, but let's be intelligent and choose something that works well with those. I chose 30. You don't have to. And as we saw with the Excel demonstration, when we had a profit of $30, our objective function line was here. It intersects at x2 equals 10 and x1 equals 6. Sorry, at x1 equals 5. And because it's a minimization problem, we want to bring our profit line in, or sorry, our cost line in as close to the origin where the cost would be 0 as possible. So I can use my sliders to decrease it, move it in towards the origin. The last point in the feasible region, in this green area out here, the last point it hits before it leaves is where we're going to find our cost minimization optimal solution. And there it is at 8 bags of Crop Quick, which is $3, 0 bags of Supergirl, which is $6, which is kind of what you'd expect. And that is the end of the graphical solution for the Farmer Dave problem from class number 2.